I rented out 11 different GPUs to see which was fastest and which was cheapest. And now I'm going to show you the difference in price, time to first token, and throughput for all these different GPUs, including AMD 300X, and then various NVIDIA architectures, including Hopper, H200, H100, Lovelace, RTX 4000, 6000 ADA, and the L40S, and then the Ampere series of GPUs, which includes the RTX A4000, 6000, the 3090, which I'm going to show you live on this stream here, and also the A40, which is particularly cheap on RunPod, and the A100. And for the tests, I'm going to run the exact same thing for every GPU. I'll run 500 input tokens. There'll be some variance around that just to make the test a bit harder, but the same variance for every GPU. I'm going to run 150 output tokens, again with a small bit of variance. That'll be the average. I'll do 64 concurrent requests, so this is a fairly high load. And I'm mostly going to run with SGLang, which is a great inference library. Another great inference library is vLLM, and I'll show you a comparison later on at the end between the speeds of both. Now, for every GPU, I'll also run with two different forms of the model. I'll run in 8-bit and I'll run in 16-bit. And all of the time, I'll be running the Llama 8B 3.1 model. So same model, but I'll run it in 8 bits and in 16 bits. So here are the results, starting off with time to first token. This is if you run inference in streaming mode, the time before your very first token comes back from a single request, averaged over the 64 requests. Now, I should note that I run that batch of 64 3 times, and I report the average and then the standard deviation here in the error bars. And this is the time to that first token. So you can see for the most powerful GPUs like the H200, we've got a time to first token of just about half a second in 8-bit or 16-bit. And then generally speaking, the time to first token goes up as you move towards the older generation and the cheaper GPUs. So as you move out towards, say, the Lovelace architectures like the L40S or the L4, sorry, not L4, but the L40S, or as you move towards the Ampere architectures like the A100 here. So generally speaking, time to first token is best for the most recent GPUs, H100, H200. The A40 is quite good for a cheaper GPU that on RunPod is about just over 30 cents per hour compared to, say, $4 per hour for this one here. And then as you move to the left here, we've got slower times to that first token. Next, I want to show you the token generation throughput. So again, we have the most powerful recent GPUs giving the highest throughputs. Actually somewhat similar between the AMD GPU and the H100 and 200. What's surprising to me is I'm not getting much difference in throughput between the H100 and the 200. So that is surprising because I have many more. I've about double the flops of the H200. I've got more VRAM too, which shouldn't really matter for throughput, but a bit surprising to me, I'm not seeing more of an increase with the H200. Then moving over to the right-hand side, as we get to the earlier generation GPUs, you can see that the token throughput is falling. Notice how for some of these older GPUs, moving to 8-bit improves the throughput very significantly. And that's something I'm going to talk in detail about in the later part of the presentation. There is no BF16, there's no 16-bit inference on the A4000 just because it didn't actually fit in the memory, so I wasn't able to run inference on that. And last, possibly what you're most interested in is the price per million input tokens. So I've calculated this by dividing the input tokens by the rental price. So the input tokens per second or per hour divided by the rental price per hour. And what you'll see is that some of the earlier generation GPUs actually give the lowest cost on a $1 per token basis, whereas the more recent GPUs tend to give a higher cost, even when you factor in that they're able to give higher throughput. And I think the reason here is that you're not just paying for price per token, but with these more recent GPUs, you're getting faster inference, which is going to be valuable. It means faster response for customers, both overall in terms of the response and also the time until they see the very first token. You're also probably paying for the larger VRAM. The fact that you have larger VRAM means you can run larger models. Here, my model is only about 8 gigabytes if you're running an FP8 and about 15, 16 if you're running in the 16-bit, so that's less relevant. But the fact that these larger GPUs allow you to have less GPUs for running larger models is probably something also that you're paying for. Now you'll see in all of these three charts, I've sorted them out according to the time to first token for the 8-bit models. That's why this is increasing here, the orange bars, and I've kept the order the same in these other ones. So as you move to the right, you've got increasing time to first token, generally decreasing throughput as per this graph, but then decreasing price as well. Now just some other remarks here on the price. You can see that while the trend is generally downwards, this A40, and I'm just going off run pod pricing, so this isn't to say it generalizes across all providers, but this here is an anomaly in terms of the good value it provides, particularly at the FP8, the 8-bit type of data. It's providing a very low price of 4 cents per million input tokens here. Interestingly, you'll see as well that the A100 provides quite a good deal. It's got a meaningfully lower price per token than the newer generations, the H100 and 200. And when you look at the throughput, it's actually fairly similar. So the A100 is perhaps another good value option there. Now, I showed those in a whirlwind because I want to show you the results up front, just in case you've only a few minutes to watch the video. But I'll talk now in much more detail about a few things. I'll talk about why FP8, the 8-bit format, is really great. It's great for quality and it's great for speed. It often gets you much faster inference. I'll then walk through how I ran all of these benchmarks. And I'm going to run it on a GPU that isn't shown here. I haven't run it yet. I'm going to run it on the RTX 3090, which is a GPU some of you will have at home. It costs about €900 if you purchase one of those. Then I'll show some graphs comparing vLLM with SGLang, the two libraries, and just highlight some differences between the two in inference speed. And I'll provide a few caveats, remarks on this overall speed comparison, because it does depend on things like context length and the libraries that are used. And last of all, I'll show you how to make your own FP8 quants. The FP8 format is often available for most of the main models, but you can make your own if it's not. I recently made the quants for 5.4, so I'll show you a process, and I'll put the notebook inside the advanced fine-tuning repository for those who have access who have lifetime membership. You can also find scripts. I'll point you to those available just freely online for doing the quantization if you want to take that approach. Why is FP8 great? There's a lot of talk about 4-bit quantization, and that makes sense because 4-bit is smaller than 8 bits, so you can fit your model on smaller GPUs, and that's important if you want to run locally. But I think if you're looking at production, you should be thinking about FP8 because it provides basically no quality degradation or very little versus 16 bits. And also the GPUs are typically better set up. They're better capable to run inference in FP8. The latest GPUs can run it natively, whereas in 4-bit formats, you typically don't have GPU support. So I'll talk about what FP8 is, how does it compare to 16 or 32 bits, and then how does it compare to int8, which is an integer format that you can also use for quantizing the models. So FP8 means floating point 8. It's floating point because it's not just representing an integer, it's representing a number that has an exponent as well. Actually, if we take an example of FP8, so here's an 8-bit number 0, and you can see they're grouped 1001 and then 101. And these three groups are split apart on purpose. The first group tells you about the sign. So if it's 0, it's a positive number. If it's 1, it's a negative number. The next number tells you about the exponent. So 1001. And actually this 1001, it corresponds to the number 1, if we think in base 10, and it gives 2 to the power of 1. Now, why does it correspond to 1? Well, actually the way these 4 bits are used is to span a range that goes from -8 up to +7. And so when we're at the number here of 9, we take away 8, which is the bias. That basically allows us to take a number that would be 0 to 15 and slide it down so it fits from -8 to +7. And so when we take an exponent of 9, which is 1001 in binary, we get to the number 1. And this number 1 here is then going to be used as a power, which would be 2 to the power of 1. So this is the power that we're going to use, or the exponent. And then the last group here is the mantissa, which is kind of the leading number. So you have a leading number, and then you have 2 to the power of the exponent. And here it's 101. And so this implies a leading 1. So it's 1.101 in binary. And so if you look at the full representation here, you have the exponent 2 to the power of 1, 1 is the exponent, times 1.1001. And this is the binary floating point number, which in decimal, if you calculate it through, is 3.25. So if you want more accuracy, what you would do is you would need more bits to represent the exponent if you want to represent a larger range. And if you want a more accurate mantissa, the leading number, you would need more bits to represent the mantissa here. And the choice with FP8 is to keep one of the 8 for the sign. You always do that typically. And then have 4 in this case for the exponent and 3 for the mantissa. So this is called E4 and then M3. You can also have E5 if you want to keep 5 for the mantissa and then M2, which would give you a bigger dynamic range in the exponent, but it would restrict you to having less precision then on the mantissa. So if you look at FP8, how does it compare to 16 or 32-bit formats? Well, let's start with the 32-bit format. 32 is kind of the original format. I guess 64 is common as well. 32 will assign 1 sign bit, 8 exponent bits, and then 23 mantissa bits for a total of 32. And then kind of one of the original 16-bit formats was FP16, which is 1 sign bit, 5 exponent bits, and 10 mantissa bits. So it reduces the precision on the exponent and reduces it on the mantissa. Then there's BF16, which is brain float 16. And the idea with brain float 16 is to say, actually, the dynamic range is what really matters. So let's keep the same dynamic range as FP32. Let's keep that at 8. And let's just sacrifice more on the mantissa because probably 7 bits of mantissa is enough. So that was the idea with BF16. And that's why you'll hear people say BF16 is better for precision in language models. And it typically is just because it matches the exponent bits, which turns out is a better choice because it gives you that dynamic range that's important for capturing very large and very small values. So these are the common formats, and these are supported on GPUs after Turing. So if you look at NVIDIA, if you look at Ampere, like the A100, that's going to support 16 bits, BF16. But the Turing architecture, like a Google Colab T4, is not going to support brain float 16. So you'll just have to use FP16. And then if you move on to FP8, the idea is, well, can we sacrifice a bit versus the 16-bit and also on the mantissa bits, but get a more compact data format? And as I said, there are 2 common types of FP8. There's E5M2, which is 5 exponent, and E4M3, which is 4 exponent. And there's not really a standardized use of one or the other. They're both kind of used, and often both are supported. But yeah, the idea with FP8 is that you're just using a more compressed form of data. Now, there's also FP4, which is supported by Blackwell. I actually didn't test a Blackwell. That would be a B100 or maybe B200 as well. I just didn't have one available there on RunPod. But Blackwell does support FP4. But when you get down to 4 bits, you definitely start to affect quality. So it's not trivial that you would just go down to FP4, even if it allows for support by the latest GPUs. So I mentioned the latest GPUs, but really I suppose there's the latest and then there's the latest. The very latest being Blackwell, which you can think of as being up here, not shown on the top row because it does support FP8, but also supports FP4. But here I'm looking at the GPUs I'll test today, which include the H200, 100, both Hopper architecture, then those support, with the Lovelace, ADA Lovelace architecture, the L40S, L4, RTX, 4000 and 6000 ADA. Note that the MI300X from AMD also does support FP8, but the Ampere architecture, the A40, A100, and the RTX A6000 and 4000, they do not support FP8 natively. So that means they can only do the calculations in 16 bits, which I'll talk about right now. So if you're operating on Hopper or Lovelace, or if you're on the MI300X, then we'll store and load the weights in FP8, and the compute will also be in FP8. So you're doing multiplications in this data type. But if you're on Ampere, you can store and load the weights in FP8, and I'll talk about why that's still very helpful. But for the calculations, you have to expand to 16 bits and compute in 16 bits deep inside the GPU. And how that works, if you use FP8 on Ampere, is you load your weights in 8 bits. So it means they're faster to download from Hugging Face. They're faster to load into VRAM because they're smaller, half the size. And when they are needed, they are loaded in FP8 as well onto the GPU. But in the GPU, they're actually expanded at the same time the calculations happen. There's basically an extra calculation that will expand them out to 16 bits so that multiplication can be done. And the reason this is still helpful in improving speed is because often you have a bottleneck here of moving weights in and out of the deep cache here. And the smaller your weights, the less you have to transfer in. So that's going to be good because it allows for speed up where bandwidth is the bottleneck. Now, the cost associated is that you do have to do extra calculations for expanding up to 16 bits. But if you design your kernels, which is basically the setup for the calculations inside here, if you design your kernels well, you can minimize the impact of this expansion. On one further technical note, this expansion here, which adds calculation or adds compute requirement, it won't really hurt you if you have a low batch size, because your bottleneck on low batch size is the speed of getting weights in and out of the deep cache. But it will start to hurt you as you get to large batch size because you're adding extra calculations. So large batch size, you will have less of a benefit on Ampere with using FP8, but small batch size, you'll still get a fairly big benefit. And we've already seen some of those benefits with FP8 in the results. Now, just a quick note on FP8 versus int8. Int8 is where you're just working with integers going from -128 up to +127. Whereas FP8, as I said earlier, it's got a sine, exponent, and mantissa. It's a base 2 scale. So FP8 is more dynamic. It's able to flex up and down to a larger range, whereas you're just fixed on a linear scale if you're using int8. And this means you get less accuracy if you used an int8 data type. It's not a data type I'm going to use today, but you'll hear it talked about like int4 as well, which is the 4-bit version. And yeah, that's the problem with the integer data types. They just don't have this dynamic scale, so they tend to be less precise, and they'll have higher perplexity, or they won't have the same type of performance as if you're using 16-bit or FP8. For the next part of the video, I'm going to show you how to run inference and how to test out a 3090, an RTX 3090. That's with the Lovelace architecture. Some of you may have one of these at home. And I'm going to do that using LLM perf. So I'm going to set up an endpoint on RunPod that'll be OpenAI style, and then I'm going to hit it using a library called LLM perf, which allows me to make concurrent requests. Now, I've actually cloned this. Well, I've rather forked it. It's a public fork. You can find it on GitHub under the Trelis research org, and then LLM perf. And I've basically set things up so you can easily start RunPod endpoints, and then you can run LLM perf. So the first thing you'll need is to set up a one-click template. And you've got a few choices. There's now a template for running the AMD MI3000X. You can find it under the SGLang templates. SGLang provides a Docker template that allows me to build this one-click template very easily. So if you want to take a look at that, you can do so here. That's just, you'll have to pick the MI300, and you can see that it's using a Docker template from LMSys. And it's got the standard arguments here. You can see I'm feeding in an 8-bit model right now. But what I want to do is run on a 3090, which is an NVIDIA GPU. So I'm going to run using SGLang. And I'm going to run this Llama 3.1 instruct 8B FP8 model. So let's click that. And let's pick our 3090 for 43 cents. And let's check the template. And you can see I've selected the 8-bit model. We're going to test the 16-bit model in just a second. And I've set the context length to 8000, which I've done for all of the tests. Now, I'm going to increase the volume of the disk. It's fine if you just leave it at even 10 for the 8-bit model, but I'm going to later on top load the 16-bit, so I need to have enough space. I need a minimum of probably 30. And I'm going to expose port 8000 because that's the port that we're going to hit. So I'll set those overrides. And with that, I think we're ready to get started. So I'll click deploy on demand here, and then I can check the pods that I have active, and we're going to see the container is starting to download. Now, while that container is downloading, I'm going to git clone from Trelis research. I'm going to git clone the repo here, LLM perf, and get that onto my local. So let's head over to cursor. And here I'm going to install. So first, if you don't have UV, you can pip install UV. It'll be much faster to install. And then I'm going to pip install in editable mode. Let me increase my screen size. And actually, I'll just swap my theme for the moment so you can avoid your eyes getting killed. And next. What we're going to do is run a script that's called token benchmark ray. And what token benchmark ray does is it allows us to hit a number of concurrent requests, to hit the server with a number of concurrent requests. And it allows us to hit an OpenAI style server, which is exactly what we will have set up using the one-click template. So that's a script that's actually just in the base here, token benchmark ray, and you can check it out. Basically what it does is it prepares input chunks that are going to be a mean of 550 in size, and it'll provide some standard deviation around that size. And it will aim to generate about 150 tokens, again, with some standard deviation. And sorry, I highlighted the standard deviation there. Here's the mean output tokens, and here's the smaller standard deviation for the output tokens. And the number of requests we're going to have are 64. And the maximum number of completed requests are also 64. So we're running a batch of 64, and we're going to stop the test when 64 requests are done. Now, there is additionally a results directory that we need to specify. And I have modified the scripts so that our results are saved to a database, because then we'll be able to print out the results and show them in a graph, like the graph I showed you earlier. Now, the GPU we're going to use here is the 3090. So I've swapped that, and I think it's 48 cents. I can just check back here. If I go to RunPod, I can see it's RTX 3090 for 43 cents. 43 cents. So I'll fix that value there. And I also need to grab the pod ID. So I'll put the pod ID up here, and you can see we're hitting port 8000. And there's no API key needed if we're hitting the RunPod proxy. Now, just a warning that if you go via the proxy, it goes through Cloudflare before hitting RunPod. So it probably adds a little bit of latency, which will tend to make our inference results a tiny bit slower, notably on the first token, time to first token, than otherwise. I'm not sure exactly how much. I'm guessing in the tens of milliseconds, perhaps. Also, I've got a timeout here. That's just in case things run for too long. It should be over in much faster than 600 seconds, so I haven't hit the timeout at all. Now, I'm ready to run that, but first I need to check my pod is up and running, which it is. You can see here, we're using safe tensors. We're loading the 8-bit model, and going to load two weights. First, it's got to get them from Hugging Face. So you can see it's loaded now the first weight and the second weight, only about a second to load each one, so pretty fast. Now it's capturing CUDA graphs, which should improve the inference speed. And you can see that Marlin is being used. So what Marlin does is it actually expands up from 8 to 16 bits to use 16 bits within the core of the GPU. Marlin also works for 4-bit. So if you run a 4-bit model, it will also expand them up to 16 bits. Of course, with 4 bits, you're going to compromise more on accuracy than if you're using 8 bits. So our graphs should be generated, and we are running now on port 8000. So we're ready to hit that server. So I'll just paste in, oops, that's my RunPod pod ID. Sorry, I've done the same mistake again. And we'll paste that in, and you can see our testing is going to begin for 64 series of requests to this 3090. And actually my model name is incorrect here. So I'm going to need to run that test again. It looks like we did still get throughput. I'm somewhat surprised that the test actually ran. Let's just double check what the name of the model is. It's Neural Magic. So maybe because the model name is the same, it actually managed to work anyway. But I'll replace the name for now with the correct Neural Magic model. Let's see if we get any different result this time. So that's a second batch of requests. And I'm going to run a third batch now, just so I get some variance around my metrics. So run that exact same request. And when this request is done, I'm actually going to swap in the 16-bit model. So I'll run the 16-bit model here on the same GPU. And I'm actually going to reload the GPU. I'll just wait till this is finished. I'll allow it to reload in 16 bits. So here I'm just going to edit the pod, replace this, because I'm downloading 16-bit, I need to make sure I have enough space. So I'll click space, save, and that's going to restart. So in the meantime, we can visualize our results, and we can do that just by scrolling down here. You can inspect the database if you like by running some of these SQLite commands. I'm saving them to SQLite. But let's run the visualization script. And here we should be able to scroll up and check out the plots. So here's the first plot, time to first token. And you can see our 3090. You can ignore the BrainFloat 16 result because that one for now is not yet being run. But for the FP8, which is the model we just ran, it's actually very good. So we have a very good time to first token. It's not even that much different than the MI300 or the H200. And then if we look at the throughput, again, ignore the 16-bit model. And you can see the throughput is a little bit better, probably in the same range as the A40. It's definitely lower than these top-end GPUs, and it's also a bit lower than the A100. And then the price per token is really good. So because this is a cheap GPU and it's getting decent throughput, it's actually fairly comparable in terms of price per token to the A40. So we want to see now if we can run that using the 16-bit model. And the 16-bit model is probably just loading. It's going to load 4 shards. So download 4 shards probably and then load them onto the GPU. And they're loaded and the CUDA graphs are capturing. And in the meantime, I'm just going to make sure that I don't have any data rows for the RTX 3090 in the database. Let me remove those and inspect what is there. So I'm just going to use cursor to make sure that we don't accidentally have any 16-bit data, because I did accidentally query with the wrong model name, and I'm not exactly sure what the effect would be. So we're getting a script here with Cursor Composer just to clean RTX 3090. And I'm going to run that script here now. So yeah, we did remove 1 and we've got 2 rows left. Let's just rerun the visualization and see if it changes anything. Yeah, it's removed that row. So we did have a faulty row there. I'm not actually sure what it would have done in terms of inference when I accidentally gave the wrong model name. It's interesting that it still kind of inferenced it. So yeah, that's it's pretty much in line with, it is the same as what I did, but it removed that dud row. So by now I should be up and running with this 16-bit model, which I am, and I can now inference it. And the way I'll inference it is by making the request again. And you can see I've swapped in the correct model name this time, and my run pod ID is going to stay the same. So let's just run this here. And I'm expecting this to be a bit slower because we have larger weights. So it's going to be a bigger stress on move shuttling weights into the inner cache, even though we're not actually doing compute in FP8. Actually, sorry, I think we might be doing compute in FP8 because it's a Lovelace architecture. So I'm a bit unsure. I did see the Marlin kernels loading earlier, which would suggest that it's doing the compute in 16 bits. But Lovelace does support FP8, so that is a possibility we're actually computing in FP8. Now I'll run this 3 times. We can see here we're getting a throughput of 5,000. So I know that the H200 got over 1,000. So we're definitely not up at the H200 or 100 level. But that's to be expected because we're on a smaller, older GPU. And we're just going to run 1/3 time here so we can get some good statistics. And once we're done with that run, we'll be ready to visualize again. And now we should be visualizing the 8-bit and the 16-bit version of the 3090. So here, visualizing results, and I can check out the graphs. Sorry, that's the wrong plot here. We'll come to that later. And so here, time to first token by GPU, the 3090 is performing very well, actually, probably performing a little bit better than the A40. The price per GPU, it's also in a similar price range to the A40. Notice though that we are definitely getting better performance with the FP8 model. There's both less variance in the time to first token and a lower time to first token. And also here in terms of throughput, we're getting significantly higher throughput with FP8. It's not quite as high a ratio as the A40. So it seems like the boost in the A40 was very significant. Well, it's also very significant in the 3090, but not quite to the same degree. And it's nice that we've a little bit higher throughput as well. So this would encourage me to actually use the 3090 a bit more than the A40. The only drawback with the 3090 is that it's a smaller VRAM. So I think we only have about 24 gigabytes of VRAM if we're looking at the 3090. That's correct. Whereas we're looking at 48 with the A40. So that's what makes the A40 probably a better choice in a lot of cases. You'll have more VRAM, more video RAM for doing longer context length compared to what you could do with the 3090. Okay, so that completes our graphs with the 3090. And I said I'd show you how vLLM compares to SGLang. So let's take a quick look at some of those graphs. I've only compared on the H200 and the A40, but still that should give us a little benchmark. Here in blue is SGLang, and here in orange is vLLM. And so you can first of all see that in terms of time to first token, things are very similar for SGLang and vLLM on the H200, whereas on the A40, we're seeing that SGLang is performing significantly better. The time to first token in particular on the 16-bit model, but even on the FP8 model looks to be better for SGLang. Now, if we go to the throughput comparison, with SGLang, we're getting significantly higher throughput on the FP8, and that's the big difference. vLLM, meanwhile, is performing quite similarly if we look at the 16 bits, and on the H200, it's performing somewhat similarly as well. And then last of all, with the price comparison, pretty similar here, maybe a little bit higher on the 16-bit if you're looking at vLLM, but for the A40, we're seeing pretty comparable performance except for FP8 on the A40. So basically what this is saying is if you're running on an A40 and probably a 3090 as well, you're definitely better off for running SGLang if you're running in a large batch size. I think if you run at lower batch sizes, just anecdotally, I've done a few of those tests, there's less of a gap between SGLang and vLLM. But if you're running at large batch sizes on an A40, that's an Ampere architecture, there is a significant improvement with using SGLang. Now, there are a few caveats to highlight on all of this benchmarking I've done. First thing to note is clearly big companies, OpenAI, Anthropic, Fireworks together, Gemini. I mean, Google is even in a different category because they have TPUs, which probably provide a significant advantage in terms of cost per unit throughput. But generally, all these big companies, if you look at their pricing, and you can see, for example, Llama 8B being sold for maybe 20 cents, sometimes even 10 cents per million input tokens. The price there, and granted they are charging for output tokens, I'll comment about that in a second, but the prices indicate that clearly these companies are able to perform better in terms of throughput, or else they're making a loss, but probably they're performing better in terms of throughput than these open source libraries, which nonetheless SGLang and vLLM are very performant libraries. Now, the big companies can do better in terms of inference costs for a few reasons. I'm sure I'm missing many, but one is they simply pay less for GPUs. The prices I've showed you are the prices on RunPod. There's a margin in RunPod above what's being rented by RunPod. And then even RunPod isn't as big as these big companies, so they'll have less pricing power. So presumably the cost that's being paid for GPUs, like even a H100, I would pay $4 on RunPod, but probably the bigger companies are paying, $2 or maybe even less per H100. Second of all, they have faster inference. For a few reasons, probably. One is the ability to design custom inference engines, perhaps that skip attention in certain layers. It's known that you probably don't need to do full attention in every single layer, and you can get away with just maybe doing every second layer or every third layer, and that's going to improve inference speed. They will write custom kernels. I described the Marlin kernel, which allows you to expand from 8 to 16 bits while also doing calculations. But there are kernels that can be custom written to improve performance in general and go beyond what's in open source. Speculative decoding, that's something that is available in open source. You can do it with SGLang, I believe, and vLLM. That can provide speedups of maybe 2 to 3x by using a draft model to calculate ahead what the most likely tokens will be. And also, I'm using a batch size of 64. That's going to limit the inference speed. If you are happy with inferencing at 16 or 32, that's also going to be a lever to provide higher tokens per second. The results I showed are specific to the test setup. The input of 500 or 550 actually is quite short, and the output of 150 is quite short. If you look at the median request that's going to OpenAI, it's probably quite a bit longer. I don't know, but I'm speculating it's quite a bit longer, which would reduce the tokens per second that you get. I have ignored the output token price or cost. So the way I calculate the cost per million tokens is just by taking the rental price per second or per hour by the input tokens per second or per hour. But in practice, companies also charge for output tokens. Often the output tokens are more expensive than the input tokens. So effectively, I'm underestimating the price. So in a sense, this price would be divided between input and output tokens. So if it looks like on my graphs, I'm getting 10 cents per million input tokens. Actually, that would correspond to a price of maybe, 7 cents per million input tokens, because those companies are going to charge for output tokens as well. So actually, it depends from what direction. I think now that I say it, it's more clear if I say I overestimate price. If I say 10 cents, it might be, something like 0.7 cents because of charging separately for output tokens. Just on a side note as well, it's pretty interesting that the industry norm is to charge for million input tokens plus some price per output tokens. This makes a lot of sense if you did not have attention. If you just had feed-forward neural networks, then this kind of pricing would make sense. But actually, if you look at the flops, the number of calculations that are being done, when you send in a request, the number of flops is really going to be proportional to the number of output tokens multiplied by the number of input tokens, because every output token you generate is going to have a number of flops that's proportional to the number of input tokens, including if you have KV cache. KV cache will help, but it will still be, your cost will be proportional to input times output. And of course, the pricing is not set up so that it's proportional to input times output. It's just input plus output. So there's something off in the pricing relative to the flops cost, which is kind of interesting. And probably the pricing should be more quadratic. Like you maybe have some cost per input tokens, but then you should have some unit cost multiplier times the product of the input and output. And this is because of attention. So basically model providers right now are subsidizing long context, or they're getting very good margins. Like they're both subsidizing long context and probably getting really good margins on the shorter context. So that's just a little side note. Now, for the last part of the video, I'm going to show you how to actually make these FP8 models. I talked about why I think FP8 is pretty great. And yeah, FP4 is exciting, but it's not as obvious how we will make use of it, because I think the accuracy is more of a challenge when you go down to FP4. So I'll go through the script now. It's going to be a notebook demo, and I'm going to run the demo again on RunPod. I'm going to start up a one-click template for fine-tuning. You can find it on the public repo here, Trelis Research one-click LLMs, and just go to the one-click template. And then you can pick a GPU. If I just pick one here, you'll see the template is running PyTorch and CUDA Docker image, and it's going to start up a Jupyter notebook. So if you click deploy on demand, you're ready to go. I've actually done that just to get ready earlier. So I'll click on connect, and I'm not sure why Jupyter is not ready. Let's check the logs. Connect to Jupyter Lab. And now I'm going to upload a fine-tuning script that you will find on the quantization branch of the advanced fine-tuning repo. So I have git cloned that repo. Actually, if you go to trelis.com/advanced fine-tuning, you'll see all of the different scripts. There are very many different fine-tuning and training scripts available if you purchase lifetime access to this repository. So I've git cloned the repository, and I'm just going to go to advanced fine-tuning. And right here, I have a new script called Trelis FP8 quantization that I'm going to upload. So I've uploaded that script. I'm going to pip install UV, and I'm now going to install LLM Compressor and HF transfer for fast weight downloads. Now, LLM Compressor, you can find out more here on vLLM project. It's a project of theirs. And if you read through the documents here, it will provide full guidance around how to create quantized models. You can create 8-bit models. You can also create 4-bit weight models. And you can also create sparse models, which will throw out some of the weights. to accelerate inference. That's something pretty interesting that maybe I'll get to in a later video. The one we're focused on is the activation quantization with W8A8. And I'm just following the same guidance here, but following these scripts here for activation quantization. And you can follow through all of the instructions by yourself if you like. I'll put a link below in the description. So let me increase my screen size a little bit. I'm going to make sure that HF transfer is active for fast weight downloads. And you'll also want to log into Hugging Face so you can push the model back up to hub. Now here, the model that I quantized, and this was available since last week because I quantized it last week, it's Microsoft Phi, which by the way is not permissively licensed, so be careful about using that for commercial use. But this is a very strong model. It performs similarly to Llama 3.370B, also a recent model, although it's only 14 billion parameters in size. It uses a lot of synthetic data. Maybe that's associated with why the license is not fully permissive. But we're going to load this model using transformers in the standard mode using auto model for causal, and it will automatically be loaded to GPU and probably should be loaded in BF16. That would be the auto load type. So we can actually just go ahead and get that model to load. And once it is loaded, we're going to set up a recipe for quantization, and we're going to target the linear layers with FP8 dynamic. So this is going to swap the weights from being 16-bit down to 8-bit. And we're saying here to ignore the embeddings. And then we're simply going to rename the model and save it and save the tokenizer. And then once all of that is done, it'll take a little bit of time. We're going to push the model up to hub. Now, actually, we're not going to push the model. We're going to upload it. You can push it, but I noticed that it goes through some calculations again. So I think it's quickest if you have it saved locally just to upload the folder to Hugging Face Hub. And furthermore, we can continue on and we can run some evaluations of the model. So we can use LLM eval, so pip install LLM eval. We can load the model using vLLM. Now, first, you might want to restart the kernel just to make sure that the weights are cleared from the GPU. So you can load the model, run a quick generation test. I won't rerun it here, but you can see hopefully the output comes out here. So hello, my name is, and Helen, and I downloaded this to manage my expectations. So yeah, you can see that that simple test worked. And then we're going to run the evaluation twice. So we'll run it once on the base model here, and then we'll run it again on the saved, sorry, that was not the base model. That was the model that was quantized. And here is the original model here. So I've actually got this original BF16. I've got that swapped. And I should probably put that above it. And then down below here, I've got the FP8 model. And you can see from the results here that we're running the evaluation on grade school maths, 8K. 8K means, I think, 8K rows. But we're only running on 100 rows here. And you can see the score out of 100 is 93 with some standard error. And you can see that when we rerun it in FP8, we score 0.93 with the same standard error. So basically we're getting the same result on 100 tests. Now it may be slightly worse for FP8 if you run out the full benchmark, but basically there's very little degradation when you go down to 8 bits with this model. Now let's go up here and just take a look because our model should have loaded. Looks like it's loaded. And something I want to do here is just print model. Can I do this? Model.dtype. Yeah. So you can see it is auto-loaded in BrainFloat 16. And when we run this script here, it's going to convert those layers down to being FP8. And when all of that is done, you should be able to get to your quantized model. Let's see if I can find the model in Hugging Face. So here, if I search for Trelis, you can see, yeah, we've got Phi for dynamic FP8. I've copied the results here of the quantization. And if you look at the files, instead of being 14 billion parameters, that would be about 28 gigabytes in 16 bits. So it should be closer to 14. So here you've got, let's say 3 5s is 15 and 1 is 16. So yeah, a little bit more than 14, but still we've reduced significantly in size. And that's because we didn't quantize everything. You saw that we left out the embeddings, for example. And that's why we're above 14, but still 16 gigabytes for a 14 billion parameter model is quite a compact model. And so that rounds up the quantization to FP8. This should work for most models that are supported by Hugging Face transformers. You'll often be able to find quants on Hugging Face already if you just search for the model name and then -FP8. For example, if you have Llama 3.3 and you search for FP8, you should be able to find, there's the Llama 3.3 FP8 dynamic. And it looks like there's some neural magic organization with the -ent. There's a few neural magic organizations. I'm not quite sure. That's the enterprise one. You can find some weights here. And check from the downloads that there's no model card, which I don't like, but at least it's been downloaded. So that's maybe a good sign. And you can always check okay, that's me asking for a model card. So that's a quick overview of the quantization. If you've access to advanced fine tuning, you can find that in the quantization branch. Make sure to switch to that branch. Otherwise, I'll put a link up to GitHub to the original LLM Compressor repo, where you can find instructions there and go through it by yourself. And that's it for this overview of FP8 and testing every GPU I could get my hands on RunPod. And there are quite a few resources available. If you want to check the description below, I've put a link to the advanced fine-tuning repo where you can get the quantization scripts by purchasing lifetime access to that. You can also get access to the public fork of the LLM perf repo I use to run inference or to hit my inference endpoints. That's on the Trelis Research GitHub. And I've also got a link to the one-click LLMs repo. That's a public repo too, where you can start up one-click templates, either for fine-tuning or for running any of these models in FP8 or in 16 bits. Let me know any questions below in the comments, especially if I've made any mistakes here describing the GPUs or the data types. Cheers.